Hello once again. Thanks for joining us on Space Nuts. My name is Andrew Dunkley, your host, and it's good to have your company as always. Coming up on this episode 378, what really killed the dinosaurs? It was actually dental problems. I think that was pretty much it. We're going to find out. Also, some planets that are orbiting a star that is kind of like ours, and they're all doomed. Are we talking about ourselves or somewhere else? We'll find out about that. And some audience questions about Andromeda, gravity. We never get questions about gravity, do we? And a place called Tidbinbilla. We'll get into all of that very, very soon on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to unravel all of those mysteries is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Hello. Good to see you. Looking a bit blurry today, but apart from that, you're all good.
Yeah. And maybe you need new glasses.
Oh, it could be. Yeah. Actually, I got some new glasses not very long ago. Interesting.
Yeah.
Too.
Well, I was going to get new glasses, but then they found out something else was wrong, so we're dealing with that.
Bother.
No. Yeah. Actually, the optometrist said to me, I was going to recommend new glasses because your vision's deteriorated slightly, but now I've got a bigger fish.
Oh, right. Something bigger to deal with.
Yeah. It's pressure. The pressure in your eyes.
Yes.
Yeah, apparently mine's gone up, so we're looking into it. Boom. Anyway, you can solve that. You can solve that these days just by using drops. Apparently, well, I have.
Okay.
Seems to be working. It's all a bit weird. Anyway, I'm sure everyone needed to know that.
That's all right. As long as it stops at your eyes, we're quite happy.
Yes. Now, you've got some travels coming up, haven't you? You're a busy boy.
Yes, actually, I'm off to a place called Sea Lake in Victoria, which is a state to the south of us here. Although it's very rural Victoria. I fly to Mildura and then drive for 2 hours, and I get to Sea Lake. And there is an astronomy weekend there. It's a big festival, actually, with a few professional astronomers and lots of amateur astronomers and the general public. And a good time will be had by all. So I'm doing talk, I think, and discussion and all that stuff. But then actually the weekend after that, I'm going off to another one, and I'm off again to New Zealand. And if I remember rightly, it is the 100th anniversary of one of the astronomical societies. I can't remember which. Might be the RASNZ.
Yeah, might be.
But there again, it might be the Auckland. I'll check that. I should find out, shouldn't I, before I go? That's more than a week away, so it's way below the horizon at the moment. But it will arrive very soon.
Yeah, just don't do a US president and get Switzerland mixed up with Sweden. That wouldn't go down well.
No, I know. There's all that stuff. I was talking to some Kiwis this week, actually, or interacting with them in a meeting of space agency personnel, which took place down in Canberra. I was virtually joining that to talk a little bit about dark and quiet skies. I didn't have much to say, but it was very interesting. These are all space regulators. These are the people who make the rules. And so they want to know what satellites are doing to astronomers. So that's what my part in that was.
Yeah, well, that's a big issue at the moment. Just a little interesting statistic about New Zealand, and I hate to give them a hard time. They've had a pretty rough time of it sporting-wise of late, but I got a news report the other day from the Australian Bureau of Statistics. This might interest people in other countries, but of the New Zealand population of 5 million, what percentage of those live in Australia?
I don't know the answer to that. I'd have to guess maybe 20%. It's probably something huge.
It's about 10%. Over 500,000 Kiwis live in Australia as Australian residents. Yeah. Which is 10% of their population.
That's right.
That's actually quite a surprising number. Yeah. But you know who's moving here fastest?
I don't know.
In the greatest numbers at the moment? The Nepalese.
Oh, okay. Not from New Zealand, though.
No. The Nepalese are the ones that are...
From Nepal.
Yeah. They're moving here faster than any other nationality at the moment, which, again, quite surprised me. Enough of that. That's our little planet. Let's stick to this planet because 66 million years ago, a big rock the size of Mount Everest struck the planet at what is now the Gulf of Mexico. And, of course, we all know that was something that led to an extinction-level event, which pretty well wiped out the dinosaurs. But there's been a lot of debate, Fred, about what exactly was it that finished them off. Was it the tsunami that went around the planet 3 times? Was it the change in environment? Was it the dental plaque problems created by the vegetation that changed? Now there's a new theory which seems to have quite a bit of substance behind it.
It does, that's right. And this comes from astronomers in, actually most of them seem to be in Belgium. There's a few UK names there as well. It's a paper in Nature Geoscience, which is entitled Chicxulub Impact Winter Sustained by Fine Silicate Dust. And that really tells you the story in one. So what these scientists have done have been to look very closely at some of the deposits which we find in that boundary, which used to be called the Cretaceous Tertiary boundary. It's now called the Cretaceous Paleogene boundary because I think that's a bit more specific. It's a layer in the rock strata, and that's actually what it's that layer in which iridium was found now 50 years ago nearly, and sorry, not quite 50, probably more like 40, 41, 42 years ago. That iridium was what gave rise to the theory that this was an asteroid, and it's because iridium is mostly found in extraterrestrial bodies. And so that sort of gave the rise to it. So what's happened is a more detailed investigation of that boundary has revealed that there's some stuff in that they didn't really know about. Let me read the first little bit of the abstract for this paper. So this is the real thing. It's, as I said, in Nature Geoscience. The Chicxulub impact is thought to have triggered a global winter at the Cretaceous Paleogene boundary 66 million years ago. Yet, the climatic consequences of the various debris injected into the atmosphere following the impact remain unclear, and the exact killing mechanisms of the mass extinction remain poorly constrained. So here we present, they say, paleoclimate simulations based on sedimentological constraints. That means things they find in the boundary layer from an expanded boundary deposit in North Dakota, United States, to evaluate the relative and combined effects of impact-generated silicate dust, that's pulverized rock, basically, and sulfur, as well as soot from wildfires on the post-impact climate. And what they've found is that the distribution of silicate dust, which is fine dust about 1 micrometer to 8 micrometers in diameter, and they say that's larger than has been previously estimated. Mm-hmm. And they think that dust, because it's sort of very fine dust, could have stayed in the atmosphere for 15 years. And they are suggesting that would push down the average temperature on the surface by 15 degrees Celsius. And that's significant because the average global temperature at the moment, the average, if you average it across the whole world, is 15 degrees, plus 15. So if you push it down by 15 degrees, you've got zero, basically. Yeah. You've got freezing. And they say this would have blocked, this is another aspect of it, this would have blocked photosynthesis for the amount of time that they say this would have occurred would have been 2 years, effectively, 620 days after the impact. And so that means things wouldn't grow. If you don't have any photosynthesis, first of all, you're not churning out oxygen from carbon dioxide, because that's what photosynthesis does. But also you're stifling the plants, basically. And things that live on plants don't like not to find any plants. And they say that might have directly caused extinctions of dinosaurs and other groups that couldn't adapt to the conditions. And I'm quoting now from the Cosmos article rather than the original article, which was written by Jacinta Boulder. Sorry, go ahead, Andrew.
No, I was just saying that this is probably not a huge surprise in the scheme of things. I mean, that impact caused all sorts of catastrophic things to happen, not just, the initial impact, that rebound that happened in the Gulf of Mexico or whatever was there at that time. And the tsunami, I think, went around the world, 3 times, 5 times, some massive number like that.
Yeah, probably.
Yeah,
that's right.
And was
all
like
of that
2 miles high or some horrible number.
Yes.
What surprises me is it didn't wipe out life completely.
Oh, yes, exactly. I was just going to make that comment. You're absolutely right. The trauma that the Earth suffered because of all that. Another couple of quotes from the paper here. Simulated changes in photosynthetic active solar radiation support a dust-induced photosynthetic shutdown for almost 2 years. That's kind of what I said, but in different language after the impact. And then they go on to say, we suggest that together with additional cooling contributions from soot and sulfur, this is consistent with the catastrophic collapse of primary productivity in the aftermath of the Chicxulub impact. In other words, nothing was growing. Basically, it shut down growth. But there is a subtlety, though, which is pointed out in the Cosmos article as well, that the models that these people just sorry about that.
That's 2 weeks in a row.
It's all right. Yeah, 2 weeks in a row. Yeah. Two different relatives. The models are. They suggest that the recovery from that, so they've also modelled the recovery as well as the kind of shutdown. The recovery would have been faster in the southern hemisphere, and that apparently matches, the evidence that when you look at the evidence from the geological record, the extinctions were fewer in the southern hemisphere. So it's really a really interesting, an interesting little snippet that kind of, I guess, adds weight to their model. That if you can suggest that there'd have been a faster recovery in the south, and that's what the evidence shows, then you've got some credibility with your model. Of course, the geography of the planet was different then as well. Because a lot of the continents, the stuff that's now in the north, was at that time heading northwards rather than being as far north as it is. So the breakup of Gondwana, just to give you a bit of context there, if I remember rightly, was 160 million years ago. So that had already happened.
Right.
But the map was still not really like the Earth is today. 66 million years is plenty of time for plate tectonics to shift the model, shift the globe of the Earth.
Yeah. I imagine that impact would have had a bit of an effect on plate tectonics too.
Yeah, probably. I mean, it's thought to have stimulated volcanoes as well. That's one of the other, the other lines of research that we see in that.
Yeah, for sure.
Yeah. So, a really interesting paper. I mean, isn't it extraordinary that, 40 years after it was suggested, we're still finding out about this impact and seeing different aspects to it because of the devastation that it caused.
Yes, absolutely. And you mentioned it. The event basically took us out of the Cretaceous period into the Paleogene period.
Yep.
I read a story the other day which is of a similar ilk, that we are now, according to some scientists, in a new epoch, which they're calling the Anthropocene period.
Anthropocene, that's right.
And that is human-induced climate change. They're saying we've reached the point of no return and that we are now in a new epoch, which has been created by human intervention.
So, and future geologists will see evidence of that. They'll see a boundary of exactly the same sort of thing, except it's all soot from, industrial revolution, coal burning and fossil
things, other fossil fuels. Yeah.
Other fossil fuels, yeah, that's right. So yes, we're tinkering with our planet in a way.
We sure are.
Very good. Yeah.
No, and we can't wind it back now, so we're going to have to learn to live with it by the sound of things. But that's a fascinating story. You can read all about it in on the cosmosmagazine.com website. This is Space Nuts, Andrew Dunkley here, and Fred Watson there. Let's just take a little break from the show to tell you about our sponsor, NordVPN. As I mentioned last week, I've been on the road, so I've been staying in hotels and apartments for the last 2 weeks as we travel, firstly for a family holiday, and now I'm at a wedding for my niece. Last night we stayed in a place called Coffs Harbour, and we stayed at a little place just out of town that had the worst internet that I've experienced in recent times. It was chronically slow and everything kept dropping out. But I thought I'd try something and switched my VPN on, and all of a sudden I got a seamless connection. Now, how that works, I don't know, but my wife kept insisting on using her phone on 5G. I decided to stick with the Wi-Fi network within the confines of our apartment, and I had no trouble accessing pages and the things that I was using, and she continually had trouble accessing her pages. That's not a coincidence, I don't think. Anyway, that was because I was using NordVPN and she chose not to at that point. I'm sure she'll change her mind next time, maybe. I don't know. Anyway, we have a special offer for you as a Space Nuts listener, because NordVPN's got a special deal for you as a listener through an exclusive URL, nordvpn.com/spacenuts. Now, when you go to that URL, you'll be welcomed by a page saying that there is an exclusive deal. Save big on NordVPN, plus get an extra 4 months extra, along with Nord's 30-day money-back guarantee. So check out the deal. There's all sorts of packages available, all sorts of products that you can add to the deal if you want to take it a step further. Just click on Get NordVPN and it will give you the rundown of what you want to do. If you just want the basic service, you can get that, or if you want all the bells and whistles, you can get that too. That's what I get. I love it. I particularly love the system that basically holds on to all your passwords, the cross-platform password manager. I highly recommend that. It is a ripper. Anyway, take a look at it. I've been using it for well over a year now, and I'm very, very happy with the products that NordVPN offers, and I think you will be too. nordvpn.com/spacenuts. And click on Get the Deal. 30-day money-back guarantee, and if you sign up, you get an extra 4 months as a Space Nuts listener. That's nordvpn.com/spacenuts. Now, back to the show.
3, 2, 1.
Space Nuts.
Now, Fred, to our next story, and this involves some planets orbiting a sun that is not unlike ours, a sun-like star, if we want to call it that. But there's a little bit of a difference. We're kind of enjoying our day in the sun. These planets will not.
That's right. And you're absolutely right. This is a story about a sun-like star. So it's always, stars come in many different varieties. But whenever we talk about stars like the sun, you're kind of really talking about the sun itself as well, and what might potentially happen to it, what's happened to it in the past, and things of that sort. Because what happens to one star of one particular class and mass and luminosity is likely to happen to another one as well, according to our best understanding of stellar evolution, the way stars evolve.
What class is our star? Because I keep forgetting.
Well, it's usually called a yellow dwarf star,
right?
And that's it's kind of not a very complimentary description,
No.
but it's because it's not a giant star. Giant stars are big, and the sun will evolve into a giant star, but at the moment it's not. It's a yellow dwarf.
Yeah, it's still growing up.
It's actually it's not its growing up phase. It's in its midlife. In fact, it's almost exactly midlife, about 4.57 billion years old, and it's probably got a lifetime of around about 10 billion years.
Okay.
So the stars go through a very energetic, youthful phase where all kinds of things happen, and then they settle down to a slow, steady hydrogen burning phase, which is what the sun is in now. If I remember rightly, it's 6 million tons of hydrogen it burns every second, turning it into helium and energy. Yeah,
So it's stopped stealing cars and getting drunk, and now it's relaxed.
That's right.
Relaxing at home.
Indeed, it's got its feet up and it's reading the paper, and it will do that for another probably 4 billion years or so before it does start turning into a giant star. So what we have here,
Well, that happens to humans too. As you get older, you put on a lot of weight.
swell in all the wrong directions.
Yeah, that's right.
Yeah, just like stars do.
And get red in the face.
Yes, that's right. Sometimes you do. So the star is a star actually relatively close by. It's 57 light years away. It's one that's very, very well studied.
Okay.
There's a very famous UK Schmidt telescope image of it and its surroundings. It is called Rho Corona Borealis, which means it's in the constellation of Corona Borealis. And it's as you've said, the difference between this star and the sun is just one of maturity. So yes, we're 4.57 billion years old. Our Corona Borealis is probably more like 9 billion years old. And that means it's sort of in the last phases of its normal life. So it's a normal star at the moment, but it will continue to be a normal star, but it'll behave differently from a sun-like star. Yeah. So it will start to grow and turn eventually into a red giant, possibly with a diameter in the region of, the sun's diameter is 1 million kilometers. This one could reach 10 times that, 10 million kilometers, or maybe even 1 billion. It could go that far up to be a huge bloated star. So they estimate this will happen in something like 1 billion years. It's actually a single author paper, this, which is in it's in the Astrophysical Journal, one of the well-known journals of astronomy. Stephen Kane is the author from the Department of Earth and Planetary Sciences in the University of California, Riverside. But what makes this star even more interesting, Andrew, is that it's got 4 planets around it, or at least 4 planets. We know of 4 planets which orbit Rho Corona Borealis. They're all nearer to the planet than we are to the sun. The nearest one, in fact, the nearest 2 are well inside what would be the orbit of Mercury in the solar system. So they're very close to Rho Corona Borealis. So they're definitely doomed. Yeah. There's one about the distance of Mercury, and the furthest one is 83% of the distance of the Earth from the sun, 83% from Rho Corona Borealis. So in that regard, Andrew, as that star sits at the moment, that particular planet, Rho Corona Borealis B, D is the name of it's Rho Corona Borealis D is the name of the planet that's nearly at the same distance as the Earth is from the sun. That could be in the habitable zone. It could be in the Goldilocks zone of Rho Corona Borealis. So interesting stuff. But what has been the focus of this particular study is looking at what might happen to planets as a star grows into a red giant. And it's not just a simple kind of gobbling up, which is what you might expect. It's a lot more nuanced than that. And it may well be that there are sort of irregularities in the bloating of the parent star, and that's going to have different gravitational influences on the planets going around it. And so what they're suggesting is, yes, they may, as the star grows, simply spiral in towards the star, but that would almost certainly mean that they just, because the temperature of the gaseous envelope that they're falling into is high, they just basically evaporate. They could also, it depends just on the geometry. There is something called the Roche limit, which is it's basically a point around any object in space, and the Earth has a Roche limit as well. You put something within that limit, and it cannot stay in one piece. The difference in gravity between one side of it and the other is going to pull it to pieces. That's the basis of the Roche limit. And so it's almost like spaghettification in a black hole. It's that kind of phenomenon.
Yeah.
The fact that things are getting stretched. So you try and stretch a planet and it basically falls to bits. So they may just evaporate, or they may get torn apart by the gravitational effects of it reaching the Roche limit. There's one caveat though, that is if you've got bigger objects, then there's a chance that you might influence the orbit of that planet in such a way that it actually gets thrown out of the system. It's possible that
it becomes a rogue planet.
Yeah, that's right. That its orbit kind of starts stretching and pushes it further away from the star, which may, it probably depends on there being other planets there that we don't know about yet as well. You could have interactions between those, which might then cause this, something to be thrown out. So, that would be a really interesting possibility. This paper actually looks in great detail about the possibilities for planets to escape, depending on their exact orbit. It's a very detailed report first of all, the original paper that I mentioned, but also there's a Universe Today article on it, that excellent website, which gives us space and astronomy news, and it really pulls this whole thing to pieces in a very detailed way. So what are the chances? Well, maybe there'll be the prediction for that system, which actually comes from the original paper, is the evolution of stars through their progression on the main sequence. That's just gobbledygook for a normal star. Expansion into a giant star and then final contraction into a white dwarf has profound consequences for the orbiting planets. Given the masses and semi-major axes, that's the distance from the parent object, of the 4 known planets, we predict that planet E will evaporate within the stellar atmosphere. Planet B will spiral in and be tidally disrupted. That means it'll be pulled to pieces. And planet C will be evaporated within the star's atmosphere. Planet D's fate is a bit less certain. That's the one that could spin out, but it'll probably be destroyed too at the end of the of one of the phases of evolution. And as I just mentioned there, it's possible that there might be other planets that haven't yet been detected. We don't know that they might survive or not.
Do we know what kind of planets these are?
No, I think at least one of them, I think, is let me just check, because there is a little table here.
Right.
But they're okay. So one of them is Jupiter-sized.
Oh, okay.
The others are super Earths, basically.
Right.
Sub-Neptune super Earths. Yeah.
Okay, so they're all bigger than us.
Yes, they are. They're all bigger than the Earth. That's right.
Okay, and yet they're closer to the star than.
Yes, that's right. That's often the case in what we see what we see in exoplanet systems. It's a really fascinating. It's a fascinating paper because it does look at possible scenarios for what might happen to us.
Oh, that's nice to know.
Yeah. In about 4 billion years' time.
Yeah.
So,
and
put it in your diary.
When it goes from being normal to, cataclysmically large and then back a white dwarf, how long does that process take?
I think it's in the region of, millions to 10 millions of years, which is pretty fast compared with the lifetime of the star of 10 billion years. So in fact, I think the earliest parts of that process start maybe a few 100 million years before it's really a fully fledged red giant. So temperatures will change and things will start happening over a long period, probably very slowly, so nobody notices at first, and then a few million years later, you think, "Oh yeah, here we are, we're in trouble now."
But let's say there is a people on one of those super Earths and they're observing their star. Would they get any telltale signs that something's about to change? Would there be a way of detecting the star saying, "All right, I'm running out of petrol, I'm going to blow up"?
Yeah. Well, yeah, there are, and I'm not an expert on stellar evolution. I've always got the basics of it in my mind, but it's a slow process. There's just a slow indication of increased radiation from the star before it really starts going pear-shaped.
So should we be putting out the welcome sign or the nothing to see here sign or whatever we can?
Well, 57 light years away, at standard sort of spacecraft rate, it's going to take them a few 100,000 years to get here. If they thought that the Earth looked like a nice juicy place to settle on. And it's an interesting thought. Of course, these planets are going to be much older than the planets in the solar system. So they might have, because the star's older, so they could have had population of species on them that simply aren't there now because of already, not just climate change, but maybe the drift of planets. Planet orbits do move very slowly over periods of tens to hundreds of millions of years. So, they might have already had problems in terms of the way their solar system has changed shape.
Okay. All we have to do is put a sign up saying we've moved into the Anthropocene period. So, if you want to come here, that's up to you, but it's not going to be very nice.
Watch out.
All right. So doomed planets. Nothing to see there. That's another one we can scratch off the visit list. You can read that story on the Universe Today website. Space Nuts, Andrew Dunkley here with Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Okay, now, Fred, time to tackle some questions. Got a couple of audio questions and then a really interesting email that came in from Duncan that I think you'll enjoy. It's got a funny story behind it. But firstly, we'll go to a question from Yash.
Hello, Andrew and Professor Fred Watson. My name is Yash, and I am living in Toronto, Canada, although I'm originally from India. I've been a big fan of your podcast for a while now, enjoying every single episode. I have a question for you. In the unlikely event that I find myself alive during the impending collision between our Milky Way and the Andromeda galaxy, I'm curious to know what I am actually going to see at that time. Also, will the collision be a lightning fast spectacle or a slow motion celestial dance-off? Moreover, is there any possibility of the Earth surviving amidst this celestial encounter, assuming that our planet remains intact? So can't wait to hear the answer. Thank you.
Thanks, Yash. Great to hear from you. I think we've had a question from Yash before. I can't, it just seems familiar to me, but we have been asked about the Andromeda collision numerous times. So I thought maybe we should revisit it because, there's a few people wondering what might happen. His middle questions probably answer the question outright. And Yash, look, if you are around for that event, please let me know how you're doing it, because that could be important for all of humanity.
Could indeed.
Because this is not going to happen for until week after next. No, a bit longer.
Yeah. 3 to 4 billion years we're talking about. Think about 3.5 billion years. So, so two big galaxies careering towards one another at high speed, a couple of 100 kilometers per second, if I remember rightly, something like that, maybe 300. It's an inevitable collision, we believe. We had results from Gaia that tally with the radial velocity results that we've got. Gaia measures the accurate positions of stars on the sort of face of the sky, as it were. The transverse velocities can be deduced from that. In other words, you can work out the true velocity of something, not just along the line of sight, which is what we call the radial velocity. And it looks as though it's an inevitable collision. It's not going to miss. So the bottom line here, Andrew, is that the scale of things that will happen in this collision, in terms of the length of time that's involved, is much, much slower than stuff on human timescales. So over a human lifetime, or even a lifetime of human history, which is maybe a few thousand years, nothing happens. Even at the heart of the collision, nothing happens. The bottom line is the space between the stars is so big that the stars themselves almost certainly won't collide. There might be a few instances where stars are captured into binary orbits, or where one star steals another star's planets, but they would, I think, be quite rare because of the amount of empty space. What's not empty, though, is the spiral arms of both these galaxies, which are pretty rich in hydrogen. And so the thinking is that as the collision evolves, there will be gravitational disturbances of this hydrogen, which will cause clouds of hydrogen to collapse and start forming stars very rapidly, and high-mass stars will live for a short time, and then they'll explode as supernovae. So we might start to see more supernova explosions than we do at the moment. So the last supernova explosion in our own galaxy that we could see, there are probably others that have been hidden from us by the dust in the Milky Way, but the last one we saw was 400 years ago. The last one in a nearby galaxy was in 1987. That was supernova 1987A in the Large Magellanic Cloud. So all of that could produce some differences to the environment, but my guess is that in general terms, the Earth would be likely to be relatively unscathed by this, unless one of the stars nearby turned into a supernova and irradiated us with subatomic particles. And that's not impossible. But the odds are that as an observer, it will be very spectacular at any given time. This nearby galaxy getting closer and closer. We wouldn't see it changing on a human timescale. We simply wouldn't see that. We would just see a snapshot of the events. But yes, imagine the Andromeda galaxy covering the whole of the southern sky. Sorry, the northern sky. Yeah, it would be pretty phenomenal, and it would cover a lot of the southern sky as well. So, and that would get more and more spectacular. But you wouldn't, on a human timescale, worry about it. If you could see it, you'd say, well, yeah, that's amazing. Yeah. And maybe it means we're colliding, and maybe things will get a bit hairy down the track, but for us, it's not going to affect us. So it's certainly not lightning fast, which is what Yash was saying. It's a long, slow process. And just a final footnote to this, there are simulations online you can check and see a video of what actually happens, what will happen. And it looks as though, there'll be a collision. The stars of the two galaxies will pass through one another, and then the spiral arms will start getting disrupted. It won't be a neat and tidy spiral galaxy anymore. But then it rebounds, and you've got, the things sort of squashing around. They pass through each other again, maybe 2 or 3 more times before settling down to a galaxy which will be devoid of hydrogen by then, because the gravitational interaction will use up all the spare hydrogen, and so all the stars start popping into supernovae. But at the end of it, of course, you get a galaxy which we now call Milkomeda.
Milkomeda. I love that.
Yes.
All right. Thanks, Yash. There's a follow-up question I just noticed that came in on an email from Jara, who wants to know, in regard to the combination of the Milky Way and Andromeda, what happens to their respective black holes? Will they merge? And then he's got a dad joke final line that says, you'd think that Jara would know. Jara would know.
Yeah.
Yeah, good one. So what happens to the black holes?
In the end, they would merge, I think. That's the general understanding, that they would merge because of their relative gravitational attraction.
Okay.
So, yeah.
Well, Jara should know now.
Yes. Fascinating thing to look forward to.
Or not. Boom, boom. Okay. Thanks, Jara, and thanks to Yash. Let's move on to a question from Buddy. I threw this one in because I thought that's an interesting question, because it creates a question in my mind, which I will ask after we hear from Buddy.
Hello, Space Nuts. Buddy from Oregon again. Okay. Here's my thought of the day. If nothing but Hawking radiation is supposed to escape from a black hole, how does gravity escape? Thanks, guys. Love your show.
Yeah,
it's an interesting thought, because we talk about gravity and black holes a lot. And my question after listening to Buddy is, does gravity actually escape from a black hole?
It's a well thought question, actually. I think the way Buddy's thinking is running is that gravity is one of the 4 fundamental forces that operate the universe. It's by far the weakest. It's clearly different from the other 3, which are electromagnetic radiation and the strong and weak nuclear forces. So the 4th fundamental force, gravity, some people have thought that there must be a quantum version of gravity, where gravity is spread by gravitons, and so gravitons will be subatomic particles. And you're right, subatomic particles don't escape from black holes, at least they're not if they're photons. And so it's a very good question. And I think because clearly gravity does escape from black holes, but what it underlines is that when it comes to gravity, it's a force field. And normally with a force field, you associate a subatomic particle with it. But the graviton has never been discovered. We know it's a force field because we know it works. We're all sitting in that force field now as we sit or stand on the surface of Earth. But if there are such things as gravitons, they clearly can escape the clutches of a black hole. And so that's it's an interesting question, Buddy. And I'll try and read up a bit more on that, because I think that's quite an intriguing idea.
Yeah, it is. It'd probably start another avalanche of black hole questions.
Why not?
We'd been able to escape them for a whole week.
Nothing escapes a black hole, Andrew. You should know that. True. We'll always be talking about black holes.
Yes, that's very true. Very true. Thank you, Buddy. We'll do some homework on that one for you, and we'll see how we go. Duncan has sent us in a text. This is a bit wordy, but it's worth it because there's a great story here. William Rudd was a mechanic servicing the backup generators at Tidbinbilla during the Apollo program. He was also a member of the local Highland band and a skilled piper. and he would often take his bagpipes to work and practice when it was quiet. One particular shift, while NASA's astronauts were busy on the moon, Tidbinbilla was the station relaying the signal from Houston to the moon. The story goes that the phone line between the control room at Tidbinbilla and the generator room was open, unbeknownst to Mr. Rudd. While merrily practicing the pipes, William was told in no uncertain terms, "They can hear you on the moon." It sounds improbable. It sounds improbable. They probably could without having a radio. It sounds improbable, and the people of Tidbinbilla said it didn't happen, but the people of Parkes were not quite so sure. So I have a theory. In those days, there would have been a manual patch board at Tidbinbilla with all its plugs and cables leading in and out of the facility. I imagine the internal communications were also patched via the same board. The feed to and from Houston was via the Intel STAT satellite. But did it go through the manual patch board to Tidbinbilla control room? And if it did, was the internal telephone system at Tidbinbilla also set up via the same board? Could it be possible that the distant and eerie sound of William's pipes was heard on the moon? That's a great question. I love those little pieces of folklore, if you like. That's good stuff.
Well, anything's possible is the answer to the question. I have heard this story before.
Have you?
Not in quite as much detail. Yes, I have, yeah. Bagpipes on the moon. It's so I can't remember who told me. I do know, a passing acquaintance, some of the people who worked at Tidbinbilla during the Apollo era, one in particular who came from the same part of Britain as I do. In fact, we used to get the same bus to school.
Oh, what?
His name is Mr. Din. I can't remember his first name. That's terrible. Anyway, we used to get the same bus to school, but 10 years apart. So, because he's older than me.
Right.
But it's, so there's lots and lots of stories. I don't know the veracity of it. Probably my best contact is actually John Sarkisian, who is a long-term member of staff at Parkes, a very, very prominent amateur astronomer, as well as a professional radio telescope engineer and support astronomer. He's written extensively on the Apollo era work of Parkes and Tidbinbilla, so he might know a little bit about it. Next time I see him, I'll ask him about it. What about the bagpipes, John?
Yeah.
Oh, well, yes, that's right. There were bagpipes on the moon.
Yeah. It's a great story. I hope it's true, just like I hope the Mr. Gorski story is true.
Yes, that's right. Yes, that's another one.
Yeah, the famous words that Neil Armstrong was supposed to have said when he set foot on the moon, "Good luck, Mr. Gorski." I'm not going to tell you why he said it. In fact, it's been proven that he didn't, but it's such a great story. I wish it was true.
Yes.
Oh, dear. Yes. But we're not going there. It's too dangerous. We'll be put out to pasture if we say that.
I think our listeners can find enough evidence.
Some will know. Some will know. There's plenty of evidence online about that one. Yeah. All right. Thanks, Duncan. That's great. That's worth investigating for sure. Don't forget, if you want to send us an email or you would like to send us a voice message, you can do that on our website, spacenutspodcast.com or spacenuts.io. There's an AMA tab at the top where you can send us emails and voice messages, or the button on the right-hand side, that little purple one. And have a look around while you're there to the various pages we offer, Astronomy Daily, etc. It's worth a look. Don't forget the shop. Christmas is coming up. Yeah, that's all I can say, really. Why would you give something from Space Nuts to somebody and smile while you're doing it? That's what I want to know. But anyway, gosh, no more to say.
They're good Christmas presents, Andrew.
They are.
People will love them. Yeah.
You could buy a book and use that to put your coffee on, or something.
Indeed,
yeah,
absolutely. Yeah.
All right, Fred. Thank you so much. We're done for another day.
That's great. We made it through another day, and we will look forward to other days in the future. Thanks again, Andrew. Take care.
Okay, you too. Fred Watson, astronomer at large, part of the team here at Space Nuts, and thanks to Hugh in the studio for And that's it from me. Thanks for your company. We'll catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.